Section 2.4, Shapes of Distributions. So far in this chapter we've been doing a lot of looking at grouping and graphing data, and one of the reasons we look at graphs for data sets is to see the shape of the data's distribution. And this is going to be important to us in later chapters. So what I want to do here is show you some important distribution shapes that I'd like you to be familiar with. So we have a bell-shaped distribution because it has that sort of bell shape to it. We have a uniform distribution where everything is the same height, or they're uniform. We have left and right skewed distributions, severely left and right skewed distributions, and the severest of left and right skewed distributions, which we call left exponential and right exponential. You might recognize those shapes as an exponential growth, exponential decay type of look from your algebra classes. And then we have a couple other ones, bimodal and U-shaped. So there's a few things that we want to note about these graphs. One is that some of them are symmetric distributions, and those are ones where the two sides of the distribution are mirror images of one another. So if we were to think about which ones fall into that category, that would be any one where the left and right are mirror images. So it looks like we have symmetric here, and this is symmetric. And then the bell-shaped and the uniform are symmetric. The uniform's symmetric in a very boring way because it's the same everywhere, but that means the left and right are mirror images of each other. That is not true for any of the ones in the middle, and typically we think of symmetric and skewed as being kind of opposite of each other. So all of these right here are left skewed, and these are all right skewed. And I just want to kind of talk about that a little bit real quick. So if you took a bell-shaped distribution and you randomly selected from somebody from that and you said where would they most likely be from, you would say the middle because that's where the tallest bars are. And a taller bar means that has a higher relative frequency or a higher frequency, and it just means it's more likely to happen. So most of the people in a bell-shaped distribution are in the middle, and as you get further away from the middle, as the bars get shorter, that means there's less and less people or items, and those people or things become less likely to be the ones chosen because there's not as many of them. So we talk about peaks and tails in these sort of curves. In a symmetric distribution, those tails balance out. In a left skewed distribution, you'll have a longer tail on the left than on the right. And if it's severely left skewed, it'll be a much longer tail on the left. In fact, no real tail on the right, more of just a drop off. And then a severe, like cliff type of drop off on the exponential type with only a tail to the left. So these are all left skewed. And then all the ones on the right are right skewed. But the thing that I want you to think about here that confuses people a little bit sometimes is if you were to randomly select somebody from a left skewed distribution, where would they most likely be? And the answer is on the right, because that's where the peak is. That's where most people are. So most of the people or items in a left skewed distribution are on the right. And that may seem kind of counterintuitive. But the reason it's called left skewed is because when you have a longer tail, when something's far away from the peak, we might refer to those as outliers. That's a term we're going to define in the next chapter. But when you have those, they're pulling on the average of the data set, and they're pulling that average away from the peak and towards where they are. And instead of saying it's that these outliers on the left are pulling the average to the left, we could say they're skewing the average to the left. And that's where the name of this comes from. We'll actually talk about that in chapter 3 a little bit more. But for now, it's important to note that the skewness of a distribution is determined by which side the tail is on. And actually, I think I meant a different word there, by which side the extremes are on. Could also use the word outliers, which officially comes to us in the next chapter, or the tails. So the tails represent extreme values. Now it's worth noting a couple other things while on this page. One of them is that a bell shape has extremes because it has tails, but because the tails are balanced by the symmetry, the mean doesn't get pulled anywhere, the average doesn't get pulled anywhere. In a symmetric distribution with only one peak, the average will be at the peak. These extremes or outliers over here are pulling the average to the right, but these extremes or outliers on the left are pulling the average to the left, and they're pulling equally hard, so then the average just stays in the middle. Another thing worth noting is that while we listed the bimodal and the U-shaped as being symmetric, they don't necessarily have to be, especially the bimodal. When a graph has more than one peak, which really, if you think about this right here, the U-shaped is bimodal too, a peak here and a peak there. We often refer on a graph to the peak as a type of mode. So when a graph has two of those peaks or two of those modes, what it usually represents is two populations mixed together. So just a quick example of that. If you look at the heights of men, they tend to be bell-shaped. So most men are close to whatever the average height is, and the taller the height, the less men there are in that category, and the shorter the height, the less men there are in that category. The same thing is true for women, but women have a different average. So if you threw together men and women into one population, you might have one peak where the average height of men is, and another peak where the average height of women is. But the other thing that can happen is your populations might not have equal numbers of men and women in them. So for example, if you looked at people who work in the United States, there's more men than women in the workforce. Maybe not a lot more, but still more. Maybe it's like 45% men versus women or something. But that still might mean a higher peak for the men than for the women because of that. So and if you had those different heights, you would lose the mirror image and the symmetry. So probably most important to remember that two peaks usually means two populations. You want to think about what's going on there. But also just to note that it doesn't have to always be symmetric distribution. If you thought about two peaks here, so what populations are thrown together, that looks like it would probably be a left exponential and right exponential population blended together, where the tails are kind of joining in the middle. So that would be a kind of a rare thing to happen. If it does, we refer to it as U-shaped. All right, so it turns out that when we look at distributions, we're going to usually be looking at the distribution of sample data we've collected, but what we're really interested in is what shape is the population that sample was taken from. So this theorem helps us to deal with that. If a random sample is taken from a population, then the shape of the distribution of the sample is approximately the same as the shape of the distribution of the population it came from. So when you're looking to figure out what kind of distribution does your population have, this theorem is saying what you should do if you have a random sample is look at what shape that is, and then it's likely that the population will be roughly the same shape. One of the things that you have to be aware of, though, is for bigger samples, you'll get good approximations. So if you have a big random sample, then you should have a good approximation of what the shape of the population is. And that's because the effects of random variation are greatly reduced. We saw that a little in the previous section. I'll show you that again on the computer in just a minute. But the larger your sample, if it's random, the less effects there are of random variation in the results. But when your sample size is small, you're getting a very rough approximation. It can be very hard to be sure of the shape of the population, and that's because there's still large effects from random variation in a small random sample. So yes, you can use a sample to try and figure out what the population is, but these notes say that's going to be harder to do with small samples than with big samples. So let me just show you a quick example of that, and then I'll kind of illustrate this on the computer for you too. So here's three different graphs that are from samples. This histogram is from a sample of size 25. This one's from a sample of size 250, and this one's from a sample of size 9,000. And in all of them, they would like us to try and identify what shape population we think they were taken from. Let's actually work this right to left, though I would actually like you to pause the video here for a moment and try and answer it. Looking at this sample, what shape do you think the population was that it came from? Looking at this sample, what do you think of the population was that this was drawn from? And then looking at this sample, what's your best guess at the population that it was drawn from? So go ahead and pause the video for a moment and use the previous page's pictures to try and help you out, but try and put a name down for what kind of distribution you think the population has for each of these samples. Alright, so hopefully you've got your answers written down by now. So here's our histogram of a sample of size 9,000. If we bring in the shapes from the previous page, I would argue that looks the most like the bell-shaped distribution. So I would say because the sample looks bell-shaped, it's my best guess that the population would also have a bell-shaped distribution. Now when I look at this one, it's a little bit tougher because it doesn't look like any of the ones on the previous page. It maybe looks a little bit like this bell-shaped distribution because the peak is kind of in the center. But on the other hand, there's some taller bars over here. On the right, there's more tall bars, and then there's this kind of tail on the left. So that makes people sometimes say, let's go with the left skewed distribution. And it's kind of hard to tell. And it's harder to know what the population is on this one because the sample size is smaller, the effects of random variation are bigger. So maybe this one is left skewed. Maybe this one is bell-shaped. And we might have a question mark on it this time. It's harder to be certain what your population shape is when you're looking at a smaller sample. So we should expect that when we drop down to a sample of size 25, this task of identifying the population from such a small sample will become even more difficult. The most common answer I see in class when I ask students to do this is left skewed. And I get that because they see this tallest bar over here on the right and then a further distance to the left than to the right hand side. So sometimes they'll say left skewed because of that. On the other hand, it's a little strange to say left skewed because this should be a tail, which would mean short bars kind of running out to nothing, and all these bars over here are taller than the bars on this side. So sometimes people, because of that, will say right skewed because there's taller bars on the left and the shortest bars are on the right. And then another answer that we'll get sometimes is maybe students will say, well, this bar is the second tallest, and then it's about an equal distance to both sides. Maybe this bar being so tall is just random variation due to the small sample size, and maybe the distribution is actually bell-shaped. So it's easiest to see what the population would be when the sample size is 9,000. It gets harder when the sample size gets smaller but still doable, and then much harder when the sample size drops to 25. So what we're going to go ahead and do is take a break right here, and we're going to look at some of these on the computer, and then we'll come back to the notes. But I want to show you how when your sample size is big, like 9,000, this is an easy task, harder but doable with sample size of 250, and seemingly almost impossible with a sample size of 25. So we'll go ahead and look at that on a computer simulation, and we'll come back and we'll fill in the rest of these notes. Alright, so we just finished trying to identify the shape of a population based on looking at samples, and we did that for the sample size of 9,000, 250, and 25. Now I want to show you how I'm going to use this program, the histogram distribution quiz from our StatSims folder, to do a similar type of practice. So I'm going to enter a sample size of 9,000, so like our easiest one that was on the right hand side of the notes. And when I click Start Quiz, it'll generate a random sample of size 9,000 from one of the 10 shapes that we saw on the previous page of the notes. And my job is to look at this and try and guess what shape it is. So this looks like a bell shape to me. It's high in the center, tails on both sides, seems roughly symmetric. Yeah, there's some weird little dips and spikes, but if I kind of smooth it out, it looks bell shaped. So I'm going to choose bell shape from here. And if I get it right, it'll just move on to the next one. If I get it wrong, it'll tell me. So we move on to the next one. It says we're 1 for 1, and it's off generating a new sample from a new population. Peak seems to be around here with a longer tail on the left than on the right. Yeah, again, some strange little spikes. That's probably just random variation. I would say this looks left skewed. Longer tail on the left than on the right, but still a pretty well formed tail on the right. So not severely left skewed, but just left skewed. Remember, the type of skew is based on the longer tail. So longer tail on the left, left skewed. This time I'm looking for that peak. Is it here? Is it there? Is it over here? Like, what's going on? There seems to be peaks everywhere, right? Well, as you get more and more data, all the bars are starting to even out a little bit more, and there's still these ups and downs, but roughly it's the same height all the way across, so that is what a uniform population looks like. This isn't the population, it's just the sample. That's why it has the bumps. I'm guessing that the population would be perfectly flat. If we say had 9 million pieces of data, we'd probably see that. Let me do this one and one more. Actually, I'll do this one and two more. Sometimes we get the same one, and this time we got the same one back to back. So this is going to be uniform again. I'll just let it pile up. Notice it's not the exact same shape as last time, but it's still roughly the same height all the way across, so I'm going to pick uniform. And then here we have something different. Looks like the peak's forming somewhere around here, and a long tail on the right, so some type of right skewed. But notice the left side this time is more of a plummet than a tail. So this time I'm going to say severely right skewed instead of just skewed to the right. And we're 5 for 5. We'll do one more. Looks like we're getting another repeat. Actually, looks like bell-shaped again. So let's just say we were 5 for 5 when we had a sample size of 9,000, and move on to a tougher challenge and see what happens when we drop the sample size down to 250. So same idea. Starts off seeming fairly easy. I think we have a spike on the left and on the right. So two peaks, but on the extreme ends, that's what a U-shape looks like. Now this is a little tougher, but it seems like maybe the peak would be around here, and then I have a longer tail on the right and kind of a quick drop on the left. So I'm leaning towards severely right skewed. Though I have to tell you, with this bar over here being a little taller, there is a bit of a concern that maybe the real peak is somewhere in the middle between like this bump and this bump. And if the peak was here, it would just be right skewed because there's not that big of a difference between the distance on the two tails. But I do feel like the peak's around here and a short, quick drop on this side, longer tail on the right. So I'm going to go with severely right skewed. And we got it. Alright, this time we have a peak forming here and a peak forming here. Two peaks, so bimodal. Not U-shaped because the peaks aren't on the very end. There's the U-shape again. Here we have a peak forming here, a quick drop to the right, a long tail on the left, so I'm going to go with severely left skewed. And we were 5 for 5, getting a lot of U-shapes, which by the way is lucky because those are the easiest ones to identify. This one, if the peak was here, maybe I'd say left skewed, but notice these are all about the same height. So don't get too distracted by this spike, which could just be random variation. When all the rest of the bars seem like they're roughly the same height, I would go with uniform. And then I see what this is. I think it may not be super clear to you because it's not totally well shaped like if our sample size was 9,000, but I have kind of a peak here and then an equal distance to the left and the right, and it looks like if you smooth it out, kind of a slow rise to the peak here and there with some symmetry to it. I feel like that's probably bell-shaped, U-shaped. Peak around here, really long on the left, quick drop on the right, severely left skewed. A little tougher now, but it seems like the peak is here with a longer tail on the left than the right, but a fairly well-formed tail on the right, so I would go with left skewed based on the longer tail on the left-hand side. And then here I would say this looks like the peak, in which case you'd say bell shape, but look at all these tall bars compared to all these short ones. I think this is a random spike just due to the random variation of a sample size of 250. So somewhere between here and here is maybe the real peak, in which case long tail on the right, shorter tail on the left, but still a substantial tail on the left. So I would go with right skewed based on that longer tail on the right hand side, and I went 12 for 12, which, to be honest with you, I don't always do on these. It's easy with a sample size of 250 to get fooled, but we had good luck here. So let's go to the sample size of 25 though and see what we have then. So there's our sample, and good luck to you, right? It's not really forming much of anything, but there does seem to be like maybe a peak here, but the real question is the peak here or over here or in between? I'm going to say it's probably somewhere in this neighborhood, and then a longer tail on the left than on the right, so I'm going to go with left skewed, but I don't feel anywhere near as confident with this sample size of 25 as I did with the others, but let's give it a try. Nope. It was actually bell-shaped. So that means the peak was probably more around here, and that if I got more data, again, this is so small, just 25 pieces, right? But if I got more data, these tails would have balanced out on the two sides. Is this bell-shaped? No. But it's a sample of size 25 with a lot of random variation in it. Is it reasonable to believe if I had more random data collected that it would have taken on a bell shape? Yeah, perhaps. Then why are the tallest bars over here? Just random variation, kind of bad luck. All right, a little better luck here, I think. We have a peak forming here and a peak forming there, so that feels like bimodal to me. Here we have most of our tall bars on this side with a little bit of a tail on the right. Again, not well-formed tails, not well-formed peaks, but this is where most of the data is, and more scattered here, so I'm thinking some type of right skewed. If the peak is around here, maybe it's severely right skewed, but this is our tallest bar, so maybe it's right exponential. But if it's right exponential, why is there such a tall bar over here? This is really a tough one. I think it's either severely right skewed or right exponential, but I'm really not positive. Based on this tallest bar here and a lot of other bars that are tall, I'm going to go right exponential and hope for the best. It was severely right skewed. So I want you to notice something. I got it wrong, and I think I'm 1 out of 3 now. So it is a lot harder at a sample size of 25, but I'm not completely lost here. Right exponential and severely right skewed are very similar guesses to each other. So even though it gets harder to be sure of what the shape is with a small sample size due to all the random variation, it doesn't mean you're necessarily lost. You should still have a decent guess, and when you miss, you should still be close to the right answer. Alright, this one's a tough one because we have this peak here, but these seem all kind of similar. If I take it that this is really the peak, I would say severely right skewed, much longer to the right than the left, but these are throwing me off on that. I'm really, to be honest with you, not that certain, and so I'm not going to go with the severely right skewed because of these tall ones. I'm going to say right skewed, but I feel like I'm kind of guessing. Yeah, it was uniform. Uniform's hard to pick up with these small sample sizes because we want to see that the bars are all the same height, but with all the random variation and such little data, there's just not time for them to really show up as being the same. But notice there's kind of a peak here, 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 and here. When there's peaks all over in a small sample, a lot of times that will be uniform. So what are we, 1 for 4? So this kind of has that uniform look a bit to it again. A lot of them on the left though. So is it right skewed or is it uniform? I don't know. I'm really not sure. I'll go with right skewed again. No, it was uniform. Let's see if we can get at least one more right. Let's see, maybe the peak is here and the tail on the left. So maybe left skewed. Severely left skewed. I was close, but I did miss. Peak here, longer tail on the right, right skewed. Yes. Alright, I'm going to stop while I'm ahead, but how ahead am I? 2 out of 7. Not doing that great, right? So it is important to see, like it says in the notes, when the sample size is smaller, there's a lot more random variation, and you're going to have a much tougher time getting these absolutely correct. Alright, let's head back to the notes and pick up from here. Alright, now that we've seen that computer simulation, let me go ahead and reveal the truth to you about these 3 samples. It turns out they were all taken from a bell-shaped population. So we identified that correctly when we had a big sample. We did have that as one of the options when our sample size was 250, but we weren't positive what the answer was going to be. And when our sample size was 25, bell-shaped was kind of the last of the 3 options we included. Most people tend to think of this as a skewed distribution. So again, the tricky thing is people aren't asking you what shape is this. There's no way that shape is bell-shaped. That doesn't look like this, right? But they're asking you what shape do you think the population this came from is, not this itself. And because this has some traits of bell-shaped, the population could be bell-shaped. And because the sample is so small, this tallest bar over here being on the right instead of the center, that could just be random variation. So that's something that we have to always consider when our sample sizes are very small, is that some features might just be a random variation in the data that we got. Alright, so let's go ahead and try and identify some shapes from some histograms and other graphs that we've done previously in this chapter. So we did this histogram for the ages of people with type 2 diabetes back in a previous section. So this is a sample, I believe, of 35 diabetics. So what shape do we think the population would be? So here's what the ages look like for the 35 people that we selected. What do we think it would be if we had all diabetics? All of the tallest bars are on the right. All of the shortest bars are on the left. So it seems to be a tail on the left, not so much on the right. I think I would say that the population is probably left skewed. and then maybe that's severely left skewed, maybe not. I'm not certain of that with this small sample size. It does kind of look severe in that the drop off is quick here. If it turns out the peak is around here in the 60s or the 70s, then I would say severely left skewed. But if the peak is more like in the 50s, then I would probably just say left skewed, because it really depends how big of a difference is there between the distance to the two edges from the peak. And with the kind of up down that's going on right here, that's probably random variation, so we're not positive where the actual peak is. But we are pretty sure what type of graph it is, that it's left skewed. We're just not sure how severe it is at this point. So a couple more examples. The graph below is the mini-tab version of the stem and leaf diagram from part C of the example in section 2.3 of the notes. So this is what that stem and leaf would look like on mini-tab, and you might not even recognize it as a stem and leaf at first because they leave off a key feature, which is that line that separates the stems from the leaves. And then they throw in some other numbers that we don't use, so that can be kind of distracting. So I'm going to go ahead and cross that off. So if you look at it now, we've got the stem and leaf diagram that we drew. When you're asked about shape, you want to think about left skewed, right skewed, not up skewed, down skewed. So it's probably better to turn it this way and look at it. And I think when we try to decide what kind of shape is the population here, this number becomes a key factor. When we see this number here and we see the peak here, there's a longer distance to the right than to the left. And so with a longer tail on the right than on the left, we should be wanting to say right skewed. However, this is kind of a small sample, and this is just one value. So now the question that we should start wrestling with is this just a random variation? If I had more data, would more stuff fill in and it would be more clear to me that yes, this is right skewed, I have a longer tail on the right than the left? Or would I maybe end up getting a value that showed up to provide some symmetry to that? If I did get another one over here to provide some symmetry, then I would think bell shape. Or what if that one wasn't there? I would probably kind of lean towards an answer something like bell shape. So because this is just one value, it's hard to conclusively know, is that a random variation that would get balanced out by other values? Or is it something that would get filled in and be a more developed tail when I got more data? And I can't really tell. Can't see the future or predict that. So right skewed is an option. So is bell shaped. And it's not that uncommon that when our sample size is small, we can't definitively say what shape we're going to go with. So we might provide a couple options. Maybe it's this, or maybe it's that. It can't be both, but we can't tell which one it is. If you do a problem and it says give your best guess, then just give one answer and then try and defend why you said that. Let's look at one final one. This is a dot plot of test scores. We saw this one in section 2.2 of the notes. And here you don't even have histogram bars, so it can be a little tricky at first. But what you want to think about is if you have a section like this right here where the data values are kind of densely packed, then if you continued to get more data and it continued to be that most of the data was landing in this section, then this is where your tall bars would form. And if this is the tall bars, then there's a much further distance to the left than there is to the right. So I would say it looks like these are left skewed. And I would lean towards saying that it's severely left skewed. Again, it's a sample and it's actually kind of a small one. But it really seems like this is where most of the data is, and it is a much farther distance to the left than the right. So I would tend to say that these test scores are severely left skewed. And from my experience, that is often how test scores turn out in college math exams. You have this kind of upper boundary locking you in at 100. You can't balance these out with scores on the other side because they're not possible, assuming that 100 is the max here. And so if you have a couple people who really kind of bomb the test, then they'll create a much longer tail on the left than on the right, and you get this severely left skewed shape. So now again, there's no way I can look at this picture and argue that that looks exactly like this. But I'm thinking, what if we got more and more and more people to take this test and it did fill out and start to form a smooth shape? What would it be? And it seems like with the density of the points here that the peak would probably be near here, and then I would have a much longer tail on the left than on the right. Okay, that wraps up section 2.4.